Okay, in this final video of this section, we are going to add, in effect, one more rule to the list of laws of what were Boolean algebra, what became the laws of propositional logic. We're going to add one more, but I'll give two forms of it, two laws to that list, which allow us to operate formally with predicate logic, and ultimately will give us the format of various types of proofs that we will want to be using. So proof by contradiction, for example, or proof by the contrapositive. So these were, as we now all know and love, the laws of propositional logic. And we've seen how we can take various compound propositions and use these rules to simplify those complex propositions. Sometimes we'll even come to the conclusion that a complex proposition is always true, in which case it's a tautology, or it might be always false, in which case it is a contradiction. Right, and we would like now to be able to see how these rules will apply to predicate logic, and we can largely do that because we're going to be connecting predicates in the same way that we connect propositions together. The main thing we need to be able to do is to work out how they interact with the quantifiers. So what happens when you take there exists, or for all, and you apply, for example, negation to it. And that's really the only interesting extra thing we need to do. So that's what we're going to do. And then we can start from there. We'll be able to describe some methods of proof. So proof by contradiction, for example. So this is going to be interactions of quantifiers with negation. So we're quantifying over some variable in some formula or some predicate, and sometimes we want to say it is not true, and then we want to be able to simplify the statement that we make. So consider a statement such as for all x, p of x. There are many statements like this. If you want to say something about all integers, then it is going to have that format. It's going to be for all x an integer, some predicate about x is true, some predicate p of x is true. It could be, for example, if you set it up correctly, p of x could say, well, given any prime number x, there's another prime number that's even bigger than it. So this captures the idea that there are infinitely many primes. And we'll see on one of the tutorial sheets exactly how to do that. Okay, well that happens to be a statement that's true, but there are plenty of statements I can make that are not true. So what we're going to want to be able to consider is what happens when I take a statement like this and I negate it. So what happens when I negate this statement? So the basic idea, I suppose, is that a lot of the time, if you've got not of something like this, you want to be able to pull the not through the quantifiers to get another statement. So another statement which is a proposition where things have been quantified over at the beginning. So, i.e., how can I rewrite not of for all x, p of x. And if I just think about this for a second, I will have an answer. So if you have a statement which is not always true, then what you're saying is that there is some example, a counterexample to it, so some occasion when it's false. So if some predicate is not always true, then there is some occasion where it is false. All right, and that is the rule. If I just now write down this back in formal predicate logic, I will have the rule I'm interested in. So if p of x is not always true, then there exists some, so this is i.e., this is equivalent to, there exists some value of x such that p of x is false. In other words, not p of x is true. And that is the rule. So not of for all x p of x is equivalent to there exists x such that not p of x. So it's a bit like when you're doing not of something and something, then when you take the not inside, then you swap an and for an or, and vice versa. It's very much the same idea. So that's one way to express it. Another way to express it would be to say that not of. So here's another way of seeing the same idea. If I want to say that there does not exist an x such that p of x is true. So if there is no example where some predicate holds about x, then that amounts to saying the same thing as all x do not satisfy p of x. Okay, so this is one way of saying it. This is another way of saying it. Yet another one is actually to do this together. So from this, if I do both together, taking not and not of there exists x such that p of x is true, that would tell me that there is, so for all x not p of x, and if I do that again, I do indeed get what I started with. So this fact is another way of expressing the law of the excluded middle, as it's sometimes called. Okay, let's do an example of of this, and then that will do for this section. So let me find the question I want to do. Right, so we're going to look at, so I have one example, and there are a couple more in the notes, and there will certainly be some more on the tutorial sheets. So let's consider so we're going to have a predicate of the following form. Let's consider predicates P of x and Q of, so P of x is going to be something that just depends on one variable. Q of x is going to be something that depends on two. And I'm just going to combine them in some random way, and the way I'm going to combine them is this. So for all x, maybe I'll call this R of xy, just for the sake of giving it a name. So it's going to say for all x, either P of x is true, or I can find some y such that Q of x, y is true. So I'm going to try and think of an example for you like this. So in the, let's say, the real numbers, a very good example would be either x is 0 or there exists some y so that x times y is equal to 1. Right? That would be saying either you've got the number 0, or I can divide x by y, or I can find an element that multiplies with y to give you 1, so I can find an inverse of y. I can find 1 over y. So e.g. In the reals, P of x could be x is 0 and Q of xy could be x times y equals 1. And then this would be a true statement. Okay, so maybe I think that yes, that's true for the real numbers, but I want to see, I don't believe it for the integers. Indeed, it is not true for the integers, because there are only a few numbers for which you can take 1 over it and get another integer. So I want to say what not R is. So rewrite not R of x, y. So that is not of, for all x, P of x, or, and there exists y such that Q of xy I've got enough of these brackets. I think we need one more. Okay, so I can take this inside, provided I swap this for an exists and then take not of the predicate. So this is equivalent to, there exists an x such that not of this. So I'll put a not in here and then just write it down again, and then we can use the laws of propositional logic to make some more progress. Okay, right, so I've got a predicate or another predicate. So I know how to work with those. I take not of each of them and swap this over for an and. So if neither of two things are true, then they are both not true. So this is equivalent to there exists an x such that not p of x and not of this. There exists y such that q of x, y. Okay, and we can go again because we've now got a not and we've got an exists, so we've got a quantifier. So I can swap an exists for all, as long as I then take a not inside. So not p of x and for all y, not q of x, y. Okay, and that is where I'm going to stop with that. But let's just apply this idea. So we saw in the specific case I looked at earlier where p of x is the number 0, q of x is, there exists, qxy is x times y is 1. What does this say about the integers? Well, if this statement R is not true about the integers, then that means I should be able to find some integer such that the integer is not equal to 0. Well, there are plenty of those. And if I try to think of any other integer y, then when I multiply x and y together, I do not get 1. So a good example perhaps would be the number 2. If 2 is not equal to 0, correct, and no matter what integer you multiply 2 by, you're never going to get 1. So you can see that this is actually a very good way of checking that statement is not true for the integers. And that is the end of predicate logic.